Wonderful tea on a very, very chilly day. It's a pretty chilly weekend, guys. Hey, good thing, tea, we have a link. George Atwood at the Atwood's machine. George Atwood was an Englishman, and he invented this thing using a pulley system around 1780 known as, excuse me, the Atwood's machine. And it's used to demonstrate the laws of uniformly accelerated motion due to gravity. You have some experience with it from the lab that we did just the other day. And here it is. This should look familiar. We've got two masses. One of them is smaller than the other. M1, in this case, is smaller than M2. And it's a pulley system that has a string attaching the two masses. And because strings only pull, the tension here on both sides is equal, and that's going to be helpful for us later on to solve the situation. And of course, if M2 is larger, it will accelerate downwards, and so M1 accelerates upwards like that. They are linked as part of the system because the tension string pulls. Both of them are tied together in the same motion. So it was actually used to do things like, study gravity, and so we'll look and find out later, there's actually a way to use it to determine the acceleration due to gravity that we've done with video analysis and things like that. So what we're going to do is derive this, an expression for Atwood's machine, an equation, so that we can use it in the rest of our lab. This will be very, very helpful stuff. We have some assumptions first. The assumptions are that we have a frictionless pulley, massless strings, and a massless pulley. And that will enable us to come up with like the real basic bare bones, but very useful relationships that tie everything together so we can understand the concepts that are at play using Newton's second law of motion. It's the second law of motion in particular that we're going to rely on here. So M2 is greater than M1. I'm going to start by separating the problem into two pieces and then kind of merge them together. So we have a free body diagram for mass 1 and a separate free body diagram for mass 2. And by creating them and the forces that act on these objects, it'll enable us to write the equations which we can then blend together for a final result. FBD1, Fnet equals M1A. So Fnet1 equals M1A. It's the sum of the forces in the y direction. Happens to be the y direction because M1 is only going up or down. Okay, so let's draw this out. I'll draw it for M1 and then M2, and then we'll start writing the equations. Okay, well, one of the forces acting on M1 is the force of gravity. Okay, the force of gravity is acting on M1. It's its weight. So we got W equals M1G. Your book uses W. I kind of prefer F sub G, but here we go, M1G. You might as well say weight 1 because this is the M1 mass object, the massive object 1. We also have tension, and tension is going to be pulling up to support it and actually accelerate it as well. There'll be a force of tension involved, so we got T over here. So now we need to figure, because it's a smaller mass, it will accelerate in a particular direction. It will accelerate upwards is part of this system, as you've seen in the lab. What we also need to now indicate is a coordinate system. What direction is positive? And it really helps, you don't have to do this, but it helps to consider the positive direction to be aligned with the acceleration. So up here, as part of this coordinate system, I'm going to say that plus is up, which looks very familiar. And so here we go. That free body diagram for part 1 is done. Free body diagram 2, let's take a look at it for a moment. See, free body diagram 2, Fnet2 equals M2A. Again, it's the sum of the forces in the y direction. We have up and down motion here. And so what we've got is weight 2, the force of gravity, equals M2G. That's pulling down, and the tension will be pulling up on that object. because this is the heavier one in the system, we expect that the acceleration, and rightfully so, as we've seen in lab, is downward. And so get this is the change for FBD2. I'm going to align my coordinate system to follow the acceleration. Positive is downward, like that. So now it's time to write the equations that are going to be taken from the free body diagram. The free body diagrams, the forces that act on the system, uses Newton's second law, and they will actually give us the equations that we write that pertains to each individual situation. So we can do this for any kind of situation that involves forces. In this case, it happens to be this Atwood's machine, and we have the direction of force just in the vertical. We'll obviously be doing problems later on that involve horizontals as well. Okay, so what I have here, because this is the positive direction, I have T in the positive direction. Let me do it in a slightly different color. It has blue. Blue's pretty good. T minus M1G. I'd rather just write it as M1G. I could write it as W1, but it will just go right for this in terms of the mass, since we would know the mass in our lab. Okay, and this is going to equal M1A. This is why I wanted to align this, the positive coordinate system, positive direction, with A, because this is a positive A over here. If it were negative, then I'd have to make this a negative A. And it's kind of messy on that side. So we're done with FBD number 1. This is the equation that we get from it. T minus M1G equals M1A. Now we go over here to free body diagram number 2, and I notice that this is the positive direction. So now I have M2G and minus T because T is now pointing upward, the positive direction is down, equals M2A, like that. So now we have our two equations that we'll take and work with. We'll relate them together. And the object here is to solve this for A. We want to know what the acceleration of the system is as we go about this. So let's get on it, like so. All right, guy, you let's go. Oh my gosh, hey, wow, I wrote it down prior. Hey, we saved a little time, and we have some space here now. So T minus M1G equals M1A, M2G minus T equals M2A. What I'm gonna do, as we've kind of done before, there are many techniques to solve multiple equations. What I'm gonna do is just solve each of them for T and then set them equal to each other. We've done that before with relative velocity, where we had an intersection problem where two cars were meeting at a particular point. It's the same kind of technique. I realize that the tensions are going to be the same. They have to have the same tension. Newton's third law says that the tensions must be the same. So really what we have is a tug coming from M2 tugging on M1, and so in turn M1 tugs back on M2. So the T's must be equal. All right, so I'll solve this for T. On this side, we've got T equals M1A minus plus M1G, like that. On this side over here, I have negative T equals M2A minus M2G. Okay, I don't like the negative so much, so I'm going to multiply each side by -1. And what I'll have here is T equals M2G minus M2A, like that. All right. Okay, so we'll set them equal to each other. And so that means I have on this side, it's all set, M1A plus M1G equals M2G minus M2A. I'm going to collect the A's together. I want them on the same side. So I have, I'm going to move this over here by adding M2A to both sides. So we have M1A plus M2A. And I also want to collect the G terms as well. And so I would have M2G, and I would subtract M1G from both sides, minus M1G. So it looks like this. Now what I'm going to do is factor. So I have A, I could pull an A out. And this is M1 plus M2, boom, equals, let's factor out a G, M2 minus M1. We're almost there. Now I'm going to solve for A, and this whole parentheses, are M1 plus M2, are multiplied by A, so I will divide both sides by parentheses M1 plus M2, and so we get this final result here, which is A equals G times M2 minus M1 over, in fact, I will just put the over, although the G, I'm going to put the G on the outside. Well, that's kind of very smudgy, isn't it? The G could belong in the numerator, but I can also just kind of set it over here just to visually separate it, and you'll see why in a moment. And I've got M1 plus M2, like this. So what we have here is that A is some fraction of G. It's the fraction where we've got, hey, delta M, this is the difference of the two, right? And here is M total. So that stuff that you plotted before comes into play over here. We have some kind of ratio that involves the difference of the two masses and the total of the masses, and it's a fraction of G. Now you can imagine for a moment that, well, if they can measure the acceleration somehow, and what's cool about the Atwood's machine is that it moves much slower than, say, if you were just to drop an object in Earth's gravitational field. It will accelerate 9.8 meters per second squared. Well, if you keep these values close together, M2 is fairly close to M1, you can get an acceleration, and it would be much slower. It would be something that would be measurable even with basic timepieces in 1780. So a real basic wind-up clock or watch. You can do it in that case, or even maybe a hourglass or something. And you can then use that to come up with some value for G. So this is another system, besides the one that we did, to be able to calculate the acceleration of gravity, the acceleration due to gravity G, by solving this for G and working with the known values M2, M1, and if it's slow enough, you can actually measure and find the acceleration. So that's what it is. Hopefully, here's an opportunity for you to kind of take the stuff down. Here's our equation that's going to allow us to move on and use the Atwood's machine to determine some aspects of the lab. See how close that your values came to the one that was measured on Logger Pro. All right, right on, we did it. Hey, this is Morad, and it's cold, but we're feeling pretty zesty here. Hot stuff. Morad out.